So fantastic. So good afternoon, everyone. Today is the sixth lecture, and as you see that the background has been changed completely. Now we are at the university in person officially, but since we decided to go with hybrid, now the lecture also will be recorded and can be reviewed by you later on. So last time we started with special functions, and we reached to a point that we solve the two-dimensional Poisson equation, Laplace equation for a specific problem. The problem was simple. It was like two plates that they are kept at a certain potential, another plate on the lower one which was kept at another potential, and then the upper side was completely open, and we looked into the way that the potential is evolving in space, or is distributed in space and assigned in space. So, and we found this, and I think everything was clear. If you have any question regarding to that problem, that specific problem, we can review it. I did not complete the calculation because it was just simple mathematics. You could do it afterward. So looking at the values that we had for different n, so either they were 0 or they were 1, and you have to substitute it inside the series, and you could simplify it. Today we will concentrate on two different geometries. The two different geometries are cylindrical and spherical coordinates, and then we try to solve the Laplace equation, which is the aim is again finding f function, which was f of x and x prime for specific boundary condition problem. So let's concentrate on a problem which has a cylindrical symmetry, a symmetry which is cylindrical, and then we will solve the Laplace equation for that specific geometry. And indeed, don't forget that we are talking again about a place which Laplacian of f was 0, or let's say Laplacian of phi of x was 0 for that specific region. Assuming that our space, which previously we looked at the case of x, y, and z, now in this specific case, for this specific case, I assume that our system has a cylindrical symmetry, and then is given the entire this, let's say, physics is given by either rho, which is the distance here, z here, and also the angle, which if you look at the projection here, which I call it phi. So instead of working with x, y, and z, now I have new parameters, which these new parameters is rho, phi, and z. And now definitely there is a link between the two, which you know very well. So z is the same. So x is given by rho cosine of phi, and y is given by rho sine of phi, and z is identical. So if you go also otherwise, then rho is given by x squared plus y squared, and phi is given by arctan of y divided by x, and z is equal to z. Okay. That might be also helpful to understand a little bit of the property of cylindrical symmetry or cylindrical coordinate. However, I don't want to go into the deep mathematics and finding the gradient and etc. Whenever it's needed, I will jump back to the calculus and I will do the mathematics for you. So for this specific geometry, we want to solve the problem in such a way that we want to get Laplacian of phi, which is now a function of rho, phi, and z equal to 0. So the first thing that we have to do is expanding the Laplacian into cylindrical coordinate, which is given by 1 divided by rho, derivative of rho, rho d rho, plus 1 divided by rho square, derivative, second derivative of phi, plus second derivative of z. So that is essentially the Laplacian in cylindrical coordinate. All right. So let's look at the mathematics. We will get Laplacian of phi, which is 1 divided by rho, derivative of rho, derivative of rho of phi, plus 1 divided by rho square, second derivative of phi capital, plus second derivative of phi with respect to z equal to 0. So indeed, this is the problem that we have to address, and we have to find a solution for it. So don't forget, the aim is to find phi for a specific boundary condition. Okay. So what we will do, we will solve the problem in general, and then we apply the boundary conditions. So how do we solve this problem? Guys, you should know.
Separation of variables.
Separation of variables. Yes, that's perfect. So this is the approach that also we use it for a Cartesian coordinate. So in order to do this, we assume that phi of rho, phi, and z is a function, can be given as a function of rho, function of phi, and a function of z. Okay. By the way, I have forgotten to ask you this question later on. Why can we do that? How are we allowed really mathematically to assume that this is product of 3 different functions? Any thoughts, guys? No thoughts, Tarek? Gavin? No?
I mean, it does seem weird as to why you can, but I just remember doing an E&M and not looking into it as to the conditions as to why.
Yeah, that isn't weird. It is, right? How we are allowed to assume that the solution is given by the product of the 3 independent functions. The point is that, look, from the beginning, you may feel that, look, it doesn't make sense that you assume that you have 3 independent functions of rho, phi, and z, and then you are looking for a solution which can be any arbitrary. But don't forget that we are assuming that any superposition of these independent functions also can be a solution. So at the end of the day, we will do a summation on all of those variables or indices that these functions they have, and then we assume that it's C, M, N, I don't know, whatever else that you may have of R, M, chi, N, and etc. And then we assume that that's a superposition. So that superposition allows you for functions that they are not simply a product of the 3. So that can be really expanded, okay? So that's really the reason. So what we do with the separation of variables, we will look for eigenfunctions, but geometry or boundary conditions will dictate which sort of boundary those special functions they have to sum up together and giving you the expressions. So if I want to tell you in a different way, it looks like complete expansions, right? So we have special functions which they are complete. What we do, we learn those functions, but any other functions can be expanded in terms of them. This is exactly the way. So don't worry, any other functions can be expanded in terms of them, even if they are not product, okay? But it will be series. So let's substitute them inside of the Laplacian that we had. So essentially that will become derivative of rho will act only on the R, derivative of phi will act only on chi, derivative of z will act on the z only, and then I will divide both sides by phi. So simply it will be 1 divided by R and then rho d rho of rho, the partial derivative becomes direct derivative of rho of r plus 1 divided by rho square. That will become chi d2 d phi square chi plus 1 divided by z d2 of z respect to z second derivative equal to 0. Okay, so what is this function? Is a function of rho and phi. What about this one? Is a function of z. All right. So, and variables, they are completely independent. So z, rho, and phi, as we discussed, they are Cartesian cylindrical coordinates parameter. And then they are completely independent. So we have the sum of two functions which are equal to 0. So this should be a constant. That also should be a constant. Okay. That is your choice here after. What you assume that this constant will be. Is it positive or is it negative? It's your choice. And the result will be different, by the way. The result of this term that I highlighted here will also affect the result of the other side, which is the result of the first term. We have to be careful with that, okay? So for simplicity, I will consider that is kappa square, okay, square. All right? So it can be negative, but for the time being, I'm assuming that it's positive. We will discuss about the negative one as well. So we assume that this is positive and k is a real value. All right, good. So then for the z part, I have 1 divided by z, d2 of z divided by dz power of 2 equal to k square, which means that, what is the solution for this? E power of plus minus kz. Either will be exponentially increasing or exponentially decreasing. Or if you want to watch it in different formalism, it can be sine hyperbolic or cosine hyperbolic, okay? So we found the z part. Remember, that was our choice. It could have been different. It could have been negative, right? So it can be minus k square, then the result will be sinusoidal along z, sine or cosine, okay? Or e power of plus or minus I kz. All right? For the time being, we assume that along z direction, what is happening with the field, or let's say the potential, is decaying or increasing. That defines based on the boundary condition, by the way. Look at the other term. What is the other term? Is 1 divided by rho r d rho d rho of r plus 1 divided by rho square chi d phi square of chi equal to, or let's say plus k square equal to 0. Do you agree? Fantastic. So let's do a little bit of, algebra. Multiplying both sides by rho square. Then what I will get 1 rho divided by r d rho of rho d rho of r plus k square of rho square plus 1 divided by chi d2 d phi square of chi equal to 0. Same situation. What is this function? Is only function of phi. What about this one? Function of rho. Good. Fantastic. So this is a function which is independent of rho. The other one is independent of phi. The sum again is equal to 0. Then the same situation. We assume this is a constant value. So what we will get from that, we will get that 1 divided by chi d2 of chi d phi squared is equal to, here I assume that along phi, it will be a single value, so it should be minus m squared. And m is an integer if it's covering the entire of the space. What will be the result for chi? Chi will be given by e power of I plus minus m phi. And if there is no boundary on phi, m is integer. Or in general, you can say also m is integer for the boundary. When there is a bond there, you can expand it in terms of infinite number of, let's say, harmonics. Okay. For the single value, or being single value, then you know that the chi of phi plus 2 pi should be equal to chi of phi. That dictates that m should be integer. Okay. All right. Perfect. What happens with the other term now? The other term is rho divided by r d rho of r dr 0 plus k square rho square minus m square equal to 0. All right. Is a second order differential equation. And let's solve it. So we find what is the z direction. We know what is the phi direction. And now the only part that is remaining is the radial part. And we have to solve that radial part to get further information. So far, so good? Perfect. Let's do that. Okay. So let's simplify a little bit. The first term will be rho square d2 d rho square. The second term, I'm taking the derivative of this, will be rho dr d rho. I multiply both sides by rho and r capital, then I will get k square rho square minus m square r equal to 0. Do you agree? Do you agree? Perfect. Remember, we assume in this expression that k is positive, right? K square is positive. Do you agree? Here we assume that k square is plus k square, is a positive value. If it is a negative, what happens? That term sign will change only. That becomes minus k square, rho square. Okay? Remember, that's an option that we have to look for it later on. Okay. Sorry, there were a lot of noises in the room, and my hearing aids is amplifying them, and it's bothering me. Okay, so This is a second order differential equation, and we can try to solve them. But which we will do it together. By the way, we will try to solve them together. Before doing so, I would prefer to go with a dimensionless situation, which means that I will change the variable in such a way that k rho will be a new parameter for me, which I call it u. Okay. So then R is not only is not anymore function of rho, but it's function of u. All right. So then what happens with that? So if you have R, which is function of u, then you deal with the derivative of rho of RU. Then it means that you have to do the chain rule. So you have to do the derivative of R with respect to u and derivative of u with respect to R, with respect to rho. Then that will give you a kappa dr du. Since kappa is a constant, that will be simply replacing whatever we have here will with a k. Let me do that. So the first term will be rho will be u divided by k. That will be u squared divided by k squared. Then second derivative will be k squared dr du plus u divided by k. The first derivative will be k dr du plus the second one, that will be u squared. Or if you want to follow the same rule, I will go with the k squared u divided by k power of 2 minus m squared and r. Remember, this equation r is a function of u. And don't forget, u is k rho. I'm doing that just to understand the mathematics a little bit better. It's easy to not handle k always with yourself in the calculation. So that equation will be simplified into the following, which is u squared d2 of r du squared plus u dr du plus u squared minus m squared of r. So the coefficient here, they are function of u and u squared, is a second order differential equation. In order to solve it, you have to know the property of r, or let's say the property of this differential equation. And in order to understand this, you have to divide both sides by the coefficient that you do have it here, the coefficient of highest derivative. So doing that, then that leads you to dr squared du squared plus 1 divided by u dr du plus 1 minus m squared u squared r equal to 0. Okay. This differential equation is singular. Where?
U equals 0, or if the radial equals 0?
Exactly. At u equal to 0, then the differential equation is singular. Okay. And what you do, you look at the power of these and power of the derivatives. They are in the same order. So we call it regular singularity. Okay. It's not essential one. So then, in order to solve the problem, indeed, we say that the solution for R always will be summation of AI u power of I. But since there is a singularity, that will go with u power of alpha, and the expansions will happen around u0 equal to 0, around the point of singularity. If that is not true, you have some, let's say, other singularity of u0, the expansions will happen around u0 power of n, power of I. Okay, is that clear? This is a Frobenius technique, so which is essentially we are using it. All right. knowing the property of differential equation. Not necessary that it will give you the answer, but if you get an answer that is fine, then you do have it and you are not worried. So let's say the next half an hour will be only finding the series and the coefficients and then looking at the property of these functions. Okay. So then, but as we discussed, R, which is the solution to the above differential equation, can be expanded as u power of alpha summation of ai u power of I, which I start from 0 to infinity. Remember, it's important that the power series, it will be positive. Okay? It starts from 0, then 1, 2, 3, etc. Let's substitute it here. The first term is u square, second derivative of r. You have to take the second derivative of this. So the first derivative, which is r prime, will be, let me write it in this way because it's easier to handle. I from 0 to infinity, ai u power of j plus alpha. So the first derivative will be summation of I from, I will keep it for later on. We will discuss about that. AI, I plus alpha, u power of I plus alpha minus 1. And the second derivative will be summation of I, AI, I plus alpha times I plus alpha minus 1, u power of I plus alpha minus 2. All right. So the first derivative, minus 1, second derivative, minus 2. Remember, the coefficient will be multiplied together, which is somehow reminding you of factorial or gamma functions, which we will be discussing about that later on. So now let's substitute it here. So essentially, the equation that we do have is u second, u power of 2, r second plus u r power r prime plus u square minus m square r equal to 0. That's essentially the equation, and we have to substitute r and r prime and r second inside of this equation. So I starts from 0 here. What is happening with the other one? I start from 1, because the first coefficient, which will be a constant, the derivative will be 0. And for this one, I will start from 2. Okay, remember that. By any derivatives, you are killing some term. Let's say the expansion term is given by a0 plus a1 u plus a2 u power of 2. The first derivative, a0 will be gone. The second derivative, a1 also will be gone. What you end up, which will be 2 times a2. Okay, this is what I would like to consider and remind you that that's the term that they will play a role. Now let's substitute them here. It will be u second summation of I. Remember, I start from 2 to infinity. AI, I plus alpha, I plus alpha minus 1, u plus u power of I plus alpha minus 2. The second term will be u summation of I from 1 to infinity. AI, I plus alpha, u plus u power of I plus alpha minus 1, plus u square minus m square summation of I from 0 to infinity of AI u power of I plus alpha equal to 0. Good. Perfect. Pay attention to this sort of, let's say, mathematics. It's not difficult. It just requires a little bit of attention. Definitely, they will have a certain power. Okay, so the result will be u power of 0, u power of 1, u power of 2, u power of 3, and etc. And before doing so, also note that u power of alpha goes away from all of these calculations. Okay, so then it means that you will have summation of I from 2 to infinity, ai, I plus alpha, I plus alpha minus 1, u power of I essentially. Okay, because minus 2 and plus 2, they will cancel off each other, alpha goes away, plus the second term will be summation from 1 to infinity of I plus alpha, u power of I, and the last term will be two terms essentially, which will be summation of ai, u power of I plus 2, I from 0 to infinity, minus m square, summation of I from 0 to infinity of ai, u power of I equal to 0. Good. Now what I do, I will assume that the power of the series, they're identical. This is what I push for that. So let's push and make the power of the series to be identical. I don't worry about these three, sorry, because they have the same power series. If you just forget about what is going on with A0, A1, okay, then everything is fine, and then the rest it will be okay. From I power I equal to 2, they are identical, right? So if you look at the I equal to 2, so from I equal to 2, if you look at the powers, that term plays role, that term plays role, that term plays role, that term also, it should be adjusted, because for I equal to 2, the power will be u power of 4, okay? While for the rest of them, which I highlighted here, if you look at the power series, that will be u power of 2, that will be u power of 2, that will be u power of 2. Do you agree, guys? This is the only tricky part. So for I from 2 on, 2, 3, 4, 5 until n, I'm not worried, because that coefficients, they will be identical. The powers will be identical. The only problem that I do have is this term, which I have to handle it properly. And then we will come back with I equal to 0, I equal to 1, which should be considered. Okay, I'm not considering these two, but we have to come back to that equation and looking at those possible cases. Okay, in order to make the power to be identical for all of them, I assume that I plus 2 in this term is equal to, I don't know, value of n, only for that series. For the others, what I need to do is I equal to n. For that one is I equal to n. For that one is also I equal to n. I'm making the powers of series to be identical, because I know that in a certain point it will be the same. Malika, is that clear?
Yes.
Okay, because I thought that you're struggling with understanding. If you have any question, just let me know, guys. So if you do so, For I greater than, let's say greater or equal to 2, that's fine. Then the summation will be summation of n, n plus alpha, n plus alpha minus 1, u power of n, then summation of n plus alpha, un, plus summation of n. That term, I will be equal to n minus 2, that will be an minus 2, u power of n, all right? And the last term will be minus m squared, summation of an, u power of n equal to 0. Now I can take away the summation because the summation is identical for all of them. All of the powers, they are identical, which is u power of n. Then what I do have is n plus alpha, n plus alpha minus 1 plus n plus alpha minus m squared plus an minus 2. Let's go this way. U power of n equal to 0. Is that clear? This is that term, which an is identical for them. This term is that one. An also is identical. I factor out. This is that term, which an is factor out. Okay? The only term that is remaining here is this term. What we have done, I mean, it's a series expansions. Due to the derivative, the first term and second term, they will go away. So we started from the second term on, the third term on. And then now we are looking at each of them to be individually equal to 0. Do you remember that we started with the Legendre polynomial and we say that you can build up your coefficients, or let's say orthogonal function based on the power series? The same situation happens here. So the summation of infinite power is equal to 0 for any arbitrary u value. So in order to be true, then that coefficient for each individual series should be equal to 0. This brings us to this conclusion that an times, I will factor of n plus 1, then I will get n plus 1, n plus alpha power of 2 minus m squared plus an minus 2 equal to 0. Is that clear? Factor between the first and second term, factor out n plus alpha, then it will be n plus alpha minus 1 plus 1. That will become n plus alpha, multiplying by n plus alpha, that will be n plus alpha power of 2 minus m squared. From here, what I will get, an is equal to an minus 2 divided by m squared minus n plus alpha power of 2. Or if you wish, I mean, it's identical. It really depends on you. So you can write it even maybe in some places you have seen it is minus 1 an minus 2 divided by n plus alpha power of 2 minus m squared. Okay. Remember, what was the series? R expanded as a u power of alpha, summation of ai ui. I starts from 0 to infinity. Any question? Good. Edith? Clear?
What did you say happened to the n plus alpha minus 1 term?
Oh, yeah. So
I missed what you said.
yeah. So look at this term, right? You're asking about this term, right?
Yes.
Okay, let's write it down. So it will be n plus alpha. Factor these. The first term will be n plus alpha minus 1. All right. The second term will be plus 1.
Yes, I see it now. Thank you.
Yeah, of course. Good. Fantastic. Is that clear now? We will go to the second step because here what we found that, good. I find what is going on with AI, which is this, which tells me that either I have odd coefficients or I have, odd powers, or I have even powers. All right? Because every n is linked to n minus 2. True? But there is something else which I don't know. What's that? You are muted, guys. Oh, you are eating. Good, enjoy. Any thoughts, guys?
The first term, right? A0? Like
No, there's something else. How many unknown parameters do we have here? We say coefficients. Perfect. The coefficient we found. The coefficient is given in terms of m and alpha. What is alpha value? We don't know alpha value. So alpha still is an unknown parameter which you have to find it. How do you find alpha? Any thoughts? Mahtab, Tarek? Oh, Melika, you...
We like multiply something to the series so it becomes simplified.
I skipped 2 places, right?
Okay.
I did not look for A0. What is, yeah, Gavin, go ahead.
I was going to say do some sort of recurrence thing.
Exactly. It comes back from the first 2 coefficients, which I did not consider. I considered the series going on from 2 higher, okay? 2, 3, 4, and etc. So I have not considered what is happening with the first 2 terms, because the first 2 terms exist, but not, for example, for the second derivative and the first derivative, but it exists in general. So then alpha will be defined based on that. So we can look at that, is not surprising. So look at the case when n is equal to, or I is equal to 0. The same relationship applies here, because if you can go back and look at the calculation, exactly is the same. If n is equal to 0, then you will get A zero, that is 0 by default, okay? That is equal to 0. All right? Or we have n equal to 1 or I equal to 1, which the result will be A1, 1 plus alpha power of 2 minus m squared plus A minus 1, which is again 0 equal to 0. We have one of these 2 conditions. Either this or either this for n equal 0 and n equal to 1. That helps us, or these 2 equations will help us to understand what's going on with with alpha value. All right? Which one should I consider? So from this equation, we do have A0 times alpha's power of 2 minus m squared equal to 0. Can A0 be 0? No, because if A0 is 0, from this relation, A2 will be 0, A4 will be 0, A6 will be 0, all coefficients will be 0. Okay? So from this relation, we assume that A0 is not equal to 0. Therefore, alpha should be equal to plus minus m. Okay? Do you agree, guys? So then for the first case, for the first scenario, we do have alpha equal to plus minus m and A0 to not be equal to 0. Therefore, R will be given by u power of plus minus. So let's keep for the time being plus, minus, we will discuss about that, of summation of A n u power of n, which n is changing from 0 to infinity. But definitely I know that an is given by minus 1, an minus 2 divided by m plus n minus m squared. I assume positive. Negative, you can consider that also, that will be another series. Good? We will talk about this, but I want to clarify one point from the beginning. What happens if I say no? Hey guys, I don't want to follow the first expression. For the first expression, I say that A0 is equal to 0. If A0 is equal to 0, there is no restriction on alpha. Alpha is free. Okay? But then the second equation should be satisfied, which means that A1 times alpha plus 1 power of 2 minus m squared should be equal to 0. Look. Now we are following the second expression. Now we follow the second condition. What is the second condition? A1, 1 plus alpha 2 minus m squared equal to 0. We say that from the first one, the coefficient is 0. I don't care. Okay? What you will see here, definitely, if you go with the second expression, A1 should not be equal to 0. Because if A1 is equal to 0, then any odd number is 0, or any odd power is 0, any even power also you previously considered to be 0. Then it doesn't work. Okay? The solution will be trivial, which is R equal to 0, essentially. Then we are not looking for that solution. So from here, we assume that A1 is not equal to 0. Therefore, 1 plus alpha power of 2 should be equal to m squared. Then from here, alpha will be equal to plus minus m minus 1. All right. Previously, what we got as a result for alpha, alpha is equal to plus minus m. And now here we get an answer that alpha is equal to a plus minus m minus 1. Then if we choose A0 to be equal to 0, but A1 to not be equal to 0, therefore we get R to be equal to u power of alpha, which alpha now is plus m minus 1. For simplicity, I consider the plus sign. It can be the same for minus, by the way. summation of an u power of n from 0 to infinity, which an again is given by the following expression: an minus 2 divided by the coefficient now will be now m minus 1 plus, sorry guys, I have to look at the expression, plus plus n power of 2 minus m squared. So sorry, these ends will start from 1 because we assume that the 0 is 0. While previously n starts from 0, here n starts from 1.
And sorry, in the previous case, we also assumed that a1 is equal to 0. Right?
Yes, yes.
Okay.
But because if you assume, look, if you assume that a0 is not equal to 0 and alpha square minus m square is equal to 0, then definitely that term is not 0. Then you have to choose a1 to be equal to 0. Okay?
Yeah, thank you.
So, but I will tell you guys, these expression and these expression, they are identical. They're the same. Can you get that? Look at the expression. That will be u. That will be u power of m summation of n from 1 to infinity, an u power of n minus 1. All right? Then what does it mean? That when n is equal to 1, the powers of series will start from u power of 0. So why not n minus 1 change it to be equal to m? Or I don't know, j. Then that will be u power of m summation of j, which is starting from 0 to infinity, aj minus 1, plus 1, u power of j. What I have done, I just changed the series power to start from 0 now, not starting from 1. And then replacing aj, because now you are dealing with aj plus 1, then you will get minus 1, aj minus 1 divided by m minus 1 plus n, which is j plus 1 now, j plus 1 power of 2 minus m squared, which is exactly minus 1 aj minus 1 divided by m plus j power of 2 minus m squared, which this expression is identical to that expression that you had it. So it doesn't matter really which coefficient do you choose. Do you start to the series? Do you prefer to series from starting from odd function, odd powers or even powers? With this series, you will see that the series will start from even function. Okay? Is that clear? With the coefficient which always is given by u power of m or u power of minus m, depending on the value that you choose for the result. Is that clear? Okay. So now, without loss of generality, I will consider that I will start with even powers. So I will go with the case that a0 is not equal to 0, but alpha is equal to plus or minus m. So now this is the solution that I obtained. So alpha is equal to plus minus m. An is equal, or if you prefer j, doesn't matter, whatever you prefer. Aj is equal to minus 1, aj minus 2 divided by j plus m power of 2 minus or minus 1, depending on you, m squared. Plus for the case when alpha is equal to m, minus for the case that alpha is equal to minus m. And the series that we do have as a solution, which will be u power of alpha, summation of j starting from 0 to infinity, aj u power of j. Okay. We can even further simplifying this. Let's do that and see what we get as a result. Minus 1, aj minus 2. That coefficient will be j square plus m square minus or plus, depending on the value, to jm minus m squared. The m squared goes away. Oops. M squared goes away. Then you will get minus 1. aj minus 2 divided by j can be factored out. J will be j plus minus 2m. Or essentially that will be minus 1 aj minus 2 divided by j times j plus 2 alpha. Okay. All right. In books, usually people, they don't write it in this way. What they prefer, they say, okay, we know very well that I have A0. And then what I have is A2, not A1, right? Because A1, we assume that is 0. What is A2 is given by A0 with the coefficient minus 1 divided by j, which is 2 times 2 plus 2 alpha. What about A4? Which will be minus 1 A2 divided by 4 times 4 plus 2 alpha, which this is minus 1 alpha a power of, instead of A2, I will substitute it. It will be minus 1 A0 divided by 2 plus 2 alpha. Then the entire of these things is divided by 4 times 4 plus 2 alpha. Okay, so only j, which is 2n, they will stay, and the rest they will cancel out each other. Okay, the rest there will be 0. So if j is equal to n, then you will get a to n is equal to minus 1 a 2n minus 2 divided by 2n plus 2 alpha, which will be minus 1 a 2n minus 2 divided by 4 times n plus alpha. Or people usually they write in this way: u power of alpha summation of n even functions or even power. Then you will get a n u power of n. Remember, n is even here. Then the coefficient that will be an is equals simply to an minus 2 divided by 4 and n plus alpha. Okay. or you can just simply write it in this way. 2n to n, ends from 0 to infinity. We know that the others, they will be 0. Okay. All right. Let's look at the R. Now R is a function of U and can be labeled by alpha. All right. And then that is equal to of course, a series, which the series is U power of alpha, summation of n from 0 to infinity of an infinite series, which is a series of infinite coefficients, which the value is given by 2n equal to -1 a 2n minus 2 divided by 4n n plus alpha. And remember that alpha can be either plus or minus m. These series can be introduced in different platforms. I mean, Mathematica, MATLAB, or any others software platform, and even can be considered analytically as an expression. And you can look at the property of them if they are even function or odd function, which value they start, look at the zeros of them, and etc. And we call these functions or this series essentially Bessel function. And we use the symbol of J to introduce R, okay? And we call them J of alpha of U. Whenever I'm saying that I'm dealing with the Bessel function, I mean that I'm dealing with this series that you have it here, with this relation among the coefficients that you do have. Okay, so indeed, just to understand better, J of M of U is nothing more than A0, right, with U power of M at the front, U power of 0, plus A1, U power of 1, plus, sorry. We just talked about this, so this is 0, essentially. So that will be A0, U power of 0, plus A2, U power of 2, plus A4, U power of 4, plus etc. Which A0 also can be factored out, U power of M. Then will be 1 plus the second term will be A2, which A2 will be -1, A0, which will be factored out, divided by 4 multiplied by 1 plus M x U power of 2 plus, we solve the other one, which is -1 divided by 8 multiplied by 2 plus M power of 2, 1 divided by 1 plus M with the coefficient of 4 of U power of 4 plus the other term. This is the Bessel function that you deal with. That is A2, which A0 is factored out. That is A4, which is given by A2, and then A2 is expressed in terms of A0. Okay, that is the relationship that you will end up with. Questions? So, by the way, this is not the only solution. remember that if alpha is equal to plus m, that is the relationship. When alpha is equal to minus m, the result will be j minus m of u, which means that the coefficient will start from a0 u power of minus m, 1 plus minus 1 u power of 2 divided by 4, 1 minus m. If I recall well, yes, u plus the other coefficient minus 1 power of 2 divided by 8, 2 minus m, 4 times 1 minus m, u power of 4 plus the other term. That is j minus m. In our calculation, m was integer, right? That was the assumption that we had it for single being a single value in azimuthal direction. But in general, when you deal with this differential equation, this kind of differential equation, m can be any values that you want. It can be an integer, it can be a real value, a negative value or positive value. So I did not discuss about that. The Bessel function is already introduced for those sort of cases. And essentially Bessel function of half integer has a very specific property, which is very interesting to be looked into that by itself, okay? So I will give you a break, guys. It's 3:50. Please take a break. We will be coming back in about, let's say, 10 minutes or 15 minutes, guys. I see people are smiling, so it means that 15 minutes. Okay, I will see you at 4:05. Good? Cheers. Okay. So finally, I see human in a distance of, let's say, 4 meters far from me. So some people, they move to the classroom. Thank you, guys. Now, so far, we look into the radial part of Laplacian in cylindrical coordinate, and we came to the conclusion that is called a Bessel function. Okay, so, and we say that it's labeled by Jm of u and j minus m of u. Okay. These are the two solutions that we get it. And remember, as we discussed, not necessary to have integer indices. So for our case, if they were integer due to the single value, being single value in azimuthal direction. And also note that in our problem, u was k rho in the calculation. All right. That was the substitution that we have done because we want to look at the property of them. So these two, we call them Bessel functions. And essentially is a differential equation of second order. Then what you expect two different functions to be the solution. All right. So we find Jm and J minus m, but surprisingly for us, Jm and J minus m, they are linked to each other. Jm of u is linked to the Jm minus m by minus 1 power of m, J minus m of u, if m is an element of integer. Okay. All right, or maybe it's vice versa. Maybe it's vice versa. I think it's vice versa. So it's J minus m is equal to minus m J of m. Okay, so it seems that they are not fully independent, although there is an m factor here. And we are looking for two solutions that they should be completely independent. So what people they did, they built up another function, which they call it a Bessel function of the second kind. This is the Bessel function of the first kind. And this is Bessel function of the second kind, which is essentially is given by, if I remember well, it should be sine of mu, m pi. And that was a linear combination of j minus m of u. And that was a jm of u. But then there was a coefficient in the front, which was cosine of m pi minus this. So it looked like -1 power of m of jm minus 1. So if you look at that coefficient, this is essentially for integer quantity that is similar to this one. That is the other solution that we found. And that gives also a singularity. So essentially, those are really the constant coefficient. It's just a linear combination of the jm and j minus m, which you will get as a solution. So this is what people they decided to go for and define the second kind Bessel function. And we will look at the property of these two. So remember, the differential equation that we were dealing with was u second r second of u plus u r prime of u minus, if was minus or plus? I think it was plus. U square minus m square of r equal to u, u equal to 0. So then R has two solutions, jm of u and nm of u. Sure.
In the definition of nm, if you put that jm, that cosine is -1 to the power of m, and then they will not be equal.
Remember, this is true for only m, for integer quantity of m. This is a general solution. Okay, remember, this is a general solution for any m value. How, when you go and deal with m integer, you have to look at the asymptotic behavior of the function when m is tending to be going to an integer quantity. You have to look at approximation of what is happening. What is happening essentially, guys, we got two results for alpha. Alpha equal to plus m, alpha equal to minus m. It seems that for integer quantities, these two results, they are linked to each other by the above relationship. From this relationship, what you do, you build up an independent function. And this independent function still sits in the linear coefficient, linear expansion of the two, then is a solution to the Bessel differential equation. This is what people they have done. And you will look at the Jm and Nm, which they call that either second kind solution, second kind Bessel function, or the first kind of Bessel function, of Bessel function of first kind and Bessel function of the second kind. They have a different property, but remember that both of them, they are following this differential equation. They call this also Neumann function. Okay, or Bessel function of the second kind. That's a Bessel function of first kind. They are independent now. Okay, they are independent solutions to Bessel differential equation. You can just substitute it. You will see that Jm is a solution. J minus m also is a solution. The rest is just the normal coefficients that you do have. Is a constant coefficients that you do have, and it will be factored and it will be gone. All right. Okay. So remember the potential. The aim is essentially finding the potential. So the potential that we do have For the z direction, it is e power of plus minus k z. We assume k is positive. Oh, it doesn't matter. The k square was positive. What about phi direction? The phi direction was e power of plus minus m phi, which was we assume that it should be single value, so then m should be integer. And then what about the radial part? Radial part, now we do have two different solutions. Either a of let's go this way, jm of u or k rho, or nm of k rho. Good. We assume that in this calculation, the mathematics that we had, we assume that along z direction, the potential always will decrease or will increase. That's the reason that we go with exponential term. Along azimuthal direction is a single value. Along the radial direction, we got the expression based on the m and k value. So essentially, the potential that we do have can be, or let's say these functions, the entire of these functions can be labeled by m and k. They are the two parameters that we do have. As soon as you know the m and k, then the potential is defined. Else, what you have to do, you have to go with expansions of them. K can be any continuous quantity because it's showing up here. We didn't talk about the value of it. It can be positive or negative. M can be an integer quantity. So then for the m, it will go with the summation, which is m is changing from minus infinity to plus infinity. While for k, it goes to be a continuous quantity, which is dk. Okay, so that will be the expression that we will go. We will come back to this, but let's look at the property of Jm and Nm. By the way, in some books, they don't show Nm, they use the label of Ym. Don't get confused with spherical harmonics. This is a Bessel function of the second kind. In some books, they go with Ym. I'm warning you, don't get confused with the spherical harmonics. That's the reason that I'm not using Ym here. But in some mathematical textbook, people, they go with this symbol. I will stop screen sharing. I will go to Mathematica, and I will show you some of the properties of these, and we will come back with understanding what's going on with the Jm and Nm. Stop sharing. Let me screen share on this computer. I have to first open Mathematica. Zoom would like to record this computer. To record this computer screen. Okay. Oh, sorry. I have so many securities here. Yes. Oh, quit later. Let me see if I can get Mathematica here. Screen sharing. Do you see my screen now? Okay, beautiful. That was just, I made it a couple of minutes ago during the break. So in Mathematica, I'm plotting this function, and let's see what I'm doing. So Mathematica in the core, they have Bessel functions. If you type Bessel, automatically three kinds, they will show up. Ideal is a Bessel Y that I mentioned that to you guys. These look like N in our calculation. It look like Neumann Bessel function, or let's say Bessel function of the second kind. The second one is Bessel J, is the J that we introduced. The other two, we will discuss about them, Bessel K and Bessel I. Okay, forget about that. Well, let's go with the Bessel J. And if you press on the information, it will tell you what is that. Gives the Bessel function of the first kind of Jn. This is Bessel J. We do have also Bessel Y that we will be discussing about that. Okay. Wow, it's so complicated. Okay. Now I want to plot that. So plot the function that I want to plot it is Bessel kind of first, and then the index can be any value n, and then I will plot it x, and x is changing from 0 to 10 pi. You will see why I call it 10 pi. And n, I have to define it. Let's go with n0. That's a Bessel function. Let's go with a frame true. And also plot style. I will go with a directive of thickness 0.05 and maybe red, blue. Oops. Okay, so that's a Bessel function of the first kind. Bessel J, so it's essentially J0 when you plot it from 0 to, let's say, 10 pi, which is essentially 31 radian, okay? Or let's say the 31 units. And if you plot it, you will see the oscillation behavior. So it looks like sine and cosine. And look at the value when it's what is happening from 10 pi to 100 pi. It reminds you of sine or cosine function. It's just oscillating as many as it happens here. And if I have a plot range, and if you look at the domain is changing from 0.1 to minus 0.1. So if I go from 0 to 100 pi, you will see that that is happening. So you will see that the oscillation is happening really with a small deviation of the amplitude. It's almost look like a constant, is look like a sine function with a coefficient which is appearing. So that's the reason that for high value of Bessel functions or even Neumann function, people, they approximate it with sine or cosine, but having a certain amplitude at the front of it. Okay. And let's say plot range, just to make it reliable and understand. This is what I mean. It starts essentially from 1 and suddenly drops down, and you have a lot of oscillation. So in that small region, you will see that it looks like a sine or cosine function. So for the really high value of x, that can be approximated by sine or cosine. What is happening with the Bessel function of m equal to 1? Let's look at it. It seems that something interesting happens. So for the first one, this J1, it does not start from 1, it starts from 0, right? And then you will have the oscillation. Just to give you an idea, look at the two together. Now I'm plotting 0 and J1. Do you see the 0 and J1 together? So let me label them with another blue and red. Oops. Let's go with this one. So J0 starts from 1, while J1 will start from 0. Can you tell me why? A hint. Look at the series expansion. Do you remember? What it should be J0. J0 will be given by u power of 0 times the series, while J1 will go with u power of 1 times the series of itself. U2, the same story, will be u power of 2 times the series. So essentially, for any J, which is m is starting from non-zero value, you have a u power of m at the front, and u power of m, when u goes to 0, that will be a 0 value. So that's the reason that all of the Bessel functions, which they have a non-integer index, non-zero index, will start from a 0 value. Okay, so look at the others. So I can manipulate this and look at Bessel, Bessel j of n and x, and then I'm manipulating n. I'm changing n from 0 to, I don't know, 5. So that's what happens when I'm changing n. That's n equal to 0.5, n equal to 1, n equal to 1.5, 2, 2.5. You will see the 2.5 has a strange behavior, 3 that start from 0, and etc. So let's do that. I'm looking at the plot of that's what happens with Bessel function of 0, 1, 2, 3, 4, 5. So you have 6 Bessel functions. And if you go with 3 Bessel functions, 4 Bessel functions, you will see that the Bessel 0, that is Bessel 1, Bessel 2, and etc. So let's look at them. So that is Bessel 0, the blue one. The orange-like is Bessel 1, which is starting here. Now I'm including Bessel 2 as well. You will see that the Bessel 2 will go a little bit far. All right. So that's really the property of the Bessel functions. And now let's look at the Neumann or second kind Bessel function, which is Bessel of n. What? Sorry, it will be y. Yeah. You have some question? Oh yeah. Okay. So this is the property that you have for them. So let's look at the pi. I have to bring it down to plot like that. Do you see that what is happening with the Bessel function of the second kind? At the origin, it has a singularity. When u goes to 0 or x goes to 0, you will see a singularity appearing here in the calculation. What is happening with 1? The same story. You will see a singularity is hugely jumping. Okay. Let's look at the information that maybe Mathematica will help us to understand. So that is essentially what is happening with the Bessel function of y. All right. Still, it has some oscillation, but when it comes to the origin, they will be diverging. So whenever in the problem that you are dealing with, you are not including the origin, you have to bring Neumann function into the calculation. When you include origin when x equal to 0, then that function at x equal to 0 will diverge. So you have to exclude it. It looks like the exponential term. You have exponential of kx, or you have exponential of minus kx. So if let's say the term at infinity is diverging, then definitely you are not including exponential of minus kx, and vice versa. So that's the physical property that you have to be careful with Bessel functions. Now I'm going back to the calculation, and we will talk about the property of them. All right. Any questions so far? All right. Fantastic. So I will concentrate mainly on Bessel function of the first kind, and we will deal with that. Before going to the Bessel function of first kind, I would like to introduce you another differential equation, which is modified Bessel equation. And that comes from the fact that previously we assumed that along the z direction, the term that we had it for exponential term was given by positive value. So it was given by d derivative of the z with respect to z square was given by positive value. That was giving us exponential of exponential of kz or minus kz. However, if along the z direction we don't have a decaying function or increasing function, then we have to deal with some sort of oscillation along z direction. Then there we have to consider that d2 of z is equal to minus k square z. Then the term along z will be exponential plus minus kz. It will not be exponentially decaying or increasing, but now it's an oscillatory function along z direction as well. If you do have that, then the radial part of the equation as well will be modified, and any k value will be replaced by minus k square, which means that any k square rho square will be replaced by minus k square rho square. And definitely the equation that you will get will be this equation: u squared r second u plus u r prime u minus u squared plus m squared of r of u equal to 0. Okay, the point is that if you compare this to the above equation, which is that one, the only change is that u squared is replaced by minus u squared, because that u squared comes from the fact that we had k square rho square. All right, we call this modified Bessel equation, differential equation. The solutions will be two different solutions, which we call them I m of u and k m of u, which they are first kind, modified Bessel function of the first kind, modified Bessel function of the second kind. They look like J and N for these differential equation. Okay. There is an easy relationship between IM and JM, which is essentially, which is essentially what you have to do is just the argument will be replaced by a pure imaginary function. That's all. So U will be replaced by IU, and then that's the same result that you will get. Of course, you need minus I power of m at the front as well. Any questions so far? No? Okay. So let's go back to the Bessel function. So we got Jm of u, which we know very well what it starts with. And finally, as I say to you, if, for example, u is really, really large, as we discussed, the only charge is the front one. of course. U of infinity is given by, I'm cheating, by the way, guys. I'm looking at the book to tell you the value. For large value of U, as you remember that the Jm, they were oscillatory functions at the far distance for any values. So that was for Jm of U. Any others that you choose, it will be oscillatory function. So it is very realistic to approximate this with a sine or cosine. So Jm will be 1 divided by gamma of m plus 1, which essentially for integer will be m factorial of, sorry, my apologies. I'm cheating in a bad way. It will be 2 divided by pi x, which the amplitude is changing based on the x value. And then you have a cosine of x minus m pi divided by 2 minus pi divided by 4. So for large U value, essentially, Jm will be given as a cosine, while Nm will be given as a sine. Square root of 2 divided by pi x, sine of U minus m pi divided by 2 minus pi divided by 4. So that is a sine for us, because we know that sinusoidal sine and cosine, they are complete bases as well. And on the other side, they're completing each other. There are two solutions to let's say harmonic oscillator differential equation. So one is look like a sine, the other one is look like a cosine. So that is telling us that Jm and Nm, they are like sine and cosine of the differential equation that we do have for really large value of these. So there are books about the Bessel function. You can go and read about that. Myself, sometimes when I'm doing research activity, I have to go and look at the property of the Bessel functions in order to solve a problem mathematically. So as we discussed, if you look at the Bessel functions, for example, the Bessel function of J0 of x, it starts from 1, and then you have the oscillations. If you look at the J1 of x, it starts from 0, and then you have a different oscillations here. There are a number of points which the Bessel function of J0 is crossing the x equal to 0. Okay, a y equal to 0. So those points, we call them the zeros of Bessel functions. And any Bessel function has its own zeros. Okay, so those points, orange or green, we call them the zeros of Bessel function. The places that the Bessel function, the value of Bessel function will be equal to 0. So we label them by, let's say, x. One index will be m, which is indicating which Bessel function we are talking about. And the other index, I will call them k, maybe not k, let's call it them j, which means that the j's 0. So, for example, that one will be the first for the first 0 for the J0. Am I looking? Yes. This one will be the second for J0. That one will be the third, fourth, and etc. So what is happening that Jm of, remember, Jm of xmj is equal to 0. Xmj is the j's zeros of Bessel function of M. All right, is that clear? So Jn of xmj is not zero because they have a different index. All right. Fantastic. So if you look at this expression here, and usually when we say xmj, I mean, we are talking about jm. We are not talking about nm. If you want to talk about nm explicitly, you have to say or introduce, let's say, your zeros function, the zeros point that usually people, they call it ym, j. Okay, so that we can call it also n of m y mj is equal to 0. Any questions? I think we are good. So what is happening for u which they are really large, then the zeros, they will be look like the zeros of cosine function. All right, which we say for large values of the argument, then xmj is equal to n pi, or let's say j pi, sorry, j pi minus m minus 1/2 of pi divided by 2. That is approximate. So for large values, you have to look at where the cosine function will be equal to 0, and then you will find the zeros of cosine function. Those are the points that you will get the 0 values. Good, so far so good. Now let's go back and learn a little bit more about the Bessel function. So Bessel functions, they form complete bases. Bessel functions form complete bases. So which is an assignment that you do have it, that you have to prove it. But also the Bessel function in a domain that we will discuss, they will also form a complete basis. So assuming that we consider a specific problem, which we assume that the cylindrical coordinate that we choose, it's covering a certain circle. So that's the boundary that we have it. We call it A, and we define the number of zeros inside of that, and then we look at the completeness relationship. Let me look at the differential equation if I can get something interesting out of that. U prime. Okay. So you can look at your books for getting some of the properties of Bessel functions. What I want to tell that is a little bit important for people that they work in the field. So one surprising things with the Bessel function is the area in cylindrical coordinates. So if you remember, that was a Bessel of the Bessel of J0 of U. All right. So it has 0 points, as we discussed. The interesting property of the Bessel function is that integral of J0 of u du from one of the zeros, which we call them x0 of j to x0 and j plus 1. Okay. Square modulus, that is a constant. So what does it mean if I look at the Bessel function in the radial coordinate? I will see multiple rings or multiple oscillations. And when I look at this, let's say I look at the square modulus of them, what I will see that those points, they will show up as a positive value or zero value between them. But then what I will get that is for J0, so that will be a power. So, and if I look at the area that I'm covering here, the area is almost constant for all of them. So multiple rings, they will show up, but if I look at the area that they are covering, the area will be identical. And essentially, if I look at the Bessel functions, or let's say Bessel modes, that's another property. And this brings us to a very important point, that whenever you deal with the Bessel functions, they are not normalizable. So if we look at the Bessel function of J0 of u, u du from 0 to infinity, that is definitely infinity. Because you have many, many oscillations, and each of those oscillations, they are identical in terms of power, then the sum of them not necessarily will be bounded, and it will be like a plane wave, and that will be infinite value. All right, that's another important property that you have to take care of it. I may try to prove something. I'm not sure that I will get to that point, but it's worth to try. Let me just try that. We decide we did the differential equation, which was 1 divided by rho d rho of rho d rho of r plus was k squared minus m squared divided by rho squared of r equal to 0. That was a Bessel differential equation. So the result of these r was Jm of k rho or Nm of k rho. Is that clear? This is what we started with. True? So essentially 1 divided by rho d rho of rho d rho of Jm of k rho, 2 parentheses, 3 parentheses, plus k squared minus m squared divided by rho squared of Jm of k rho. This is equal to 0. Good? Good? Okay. I can multiply both sides by j. Let me think a little bit. Which sort of orthogonality I'm going to prove? Because there are three forms of orthogonality. Let me cast this m prime. If I go with m prime, or I should go with the k prime. the K prime. If I go with the K prime, it will be JM K row prime. The M goes away. That's by part that gives me the solution. Then I will get K minus K prime equal to 0. Okay, let's go with this. So Jm of K prime of rho, at least, I mean, let's start with this, what we will get. So multiply both sides with this and integrating or rho d rho from 0 to infinity. So the equation will be integral of d rho of rho d rho of Jm of K rho. All right. Then I have Jm of K prime rho d rho. The other rho goes away, cancel out each other with the denominator. Then I will get plus K squared minus M squared divided by rho power of 2, Jm of K rho, Jm of K prime rho from 0 to infinity of rho d rho equal to 0. So let's use by parts here. That will be integral of rho d rho of Jm K rho times d j u v Jm of K prime rho minus integral of 0 to infinity, that goes from 0 to infinity, of rho d rho of Jm K rho d Jm of K prime rho divided by d rho. All right. And then the other term will be plus integral of 0 to infinity of K squared minus M squared rho squared Jm K rho Jm K prime rho d rho equal to 0. Good. So, and what I can do, I can create the same expression starting from a differential equation, which is going with a K prime and multiplying by Jm K rho, doing the pi part again and doing the same expression. I get rho d rho of Jm K prime rho, Jm of K prime rho, 0 to infinity, K minus integral of rho, the same expression will appear for both of them, d rho, plus integral of K prime power of 2 minus M power of 2 divided by rho squared, Jm K rho, Jm K prime rho d rho equal to 0. Okay, substituting the two together and assuming that rho setting to be 0 and taking the derivative of Bessel function, again, will give you another Bessel function, which at infinity will be going to 0. So the term on the interval of 0 to infinity, that will be 0. The second integral, they will cancel out each other because they're identical. Inside of the integral on the third term, the M square goes away, and the only term that remains will be K squared minus K prime power of 2, integral of 0 to infinity of Jm of K rho, Jm of K prime rho, rho d rho equal to 0. And definitely for k not being equal to k prime, that term should be equal to 0. Assuming that k is not equal to k prime, therefore integral of 0 to infinity of jm k rho jm of k prime rho rho d rho is equal to 0. Okay, when k is equal to k prime, then that's a different scenario. It can be shown that when k is equal to k prime, or in general, that integral will be given by jm of k rho jm of k prime rho rho d rho, that will be equal to 1 divided by k delta of k minus k prime. All right, check these out. Maybe I have done some coefficient mistakes, but I believe that that should be the result, that it will be 1 divided by k delta of k minus k prime. So that's another form of orthogonality that you will have for Bessel functions. And that also is a completeness. All right, there's a completeness of Bessel functions with the weight of what? Rho. That's the weight that you have. If you remember, they are look like Vm, Vk prime, and they form complete basis in the entire of the space that you are dealing with. Okay, that was the completeness that we discussed last lecture. All right. Any question regarding the Bessel functions? Because next lecture will be only discussing about the physics, what is happening with the Laplace equation in different coordinates. There is no question? All right. Now let's go to cylindrical coordinates. Sorry, spherical coordinates. So in the spherical coordinates, what we have instead is not z, y, z, rho and theta, but we have r, we have phi, which is this angle, and we have theta. So we are dealing with r, theta, and phi. And the relation between these and Cartesian coordinate is very clear. Or if you want to look at the other side, you will see, remember that x was rho cosine of phi sine of theta. And then y was rho sine of phi sine of theta. And z was rho cosine of theta. That was the relationship that we had previously. So now we want to solve the Laplacian of phi equal to 0 in the spherical coordinate. So Laplacian in the spherical coordinates, let's write it down. Oh gosh. I think I have to look at the expression. I'm sure that it should be somewhere in the book, or I know the last two terms, but the first term, I'm not sure that I'm giving the proper value. Yes, I think I got that. It is 1 divided by r, second derivative of r, square of r of phi, plus 1 divided by r squared sine of theta, derivative with respect to theta of sine of theta, derivative with respect to theta of phi. And then finally, we have 1 divided by r squared sine of theta square derivative with respect to phi of phi equal to 0. That is the Laplacian that we are dealing with. Okay. Again, we have to use the separation of variables and see what we can do with it. So phi, we assume that phi is given by r of r, then a theta of theta, and chi of phi. Okay. I hope that I had not done any mistakes. So Laplacian equation can be written in the following form. Yes, it is true. That is completely true because it's one divided, okay, r square sine of theta power of 2, and then yes, that makes sense. Okay. So now let's replace it here. I will get 1 divided by r, second derivative of r, that's divided by theta and chi, so it will be 1 divided by r as well, plus 1 divided by r square sine of theta divided by theta okay, derivative with respect to theta, sine of theta, d theta of theta capital, plus 1 divided by r square sine of theta power of 2, 1 divided by chi, which is a function of phi, d2 of chi with respect to phi square equal to 0. All right. Good. What is that? Is a function of r only. This one is a function of theta and r square. This is a function of phi, theta and r square as well. We can go with the same technique that we described previously. And we know very well that if you multiply both sides by r square sine of theta square, then the last term will be only function of phi. The rest will be function of theta and rho, theta and r. Then we say that that should be a constant. And along azimuthal direction, I'm expecting to have a single value function. Then I will end up with a sine or cosine term. So this term, 1 divided by chi, d2 of chi divided by d phi square is equal to minus m square. Okay. This is what always I get from the expression. All right. Good. So we call then chi is given by e power of plus minus I m phi. Good. Then replacing inside of the equation, we get the following expression: 1 divided by r, 1 divided by r, d2 dr square of r plus 1 divided by r square sine of theta, 1 divided by theta, d theta of sine of theta, d theta of theta capital, minus m square divided by r square sine 2 of theta equal to 0. I can multiply both sides by r square. Then we get r divided by r capital, d2 dr square of r plus, that is a function 1 divided by sine theta, 1 divided by theta capital, d theta sine of theta, d theta of theta capital, minus m square divided by sine of theta equal to 0. Do you agree? I multiply both sides by r squared, and I get this expression. What is that? Is a function of theta only, and that is a function of r only. So it means that that also should be a constant. I call it this is a constant CTE. So then r divided by r d2 dr squared of r dr equal to a constant. Which means also on the other side, 1 divided by sine of theta, 1 divided by theta, d theta, sine of theta, d theta of theta capital, minus m squared divided by sine power of 2 is equal to minus that constant, because the sum should be equal to 0. How do you solve the first equation?
How about separating the derivative?
Separation of the derivatives. Usually when you deal with spherical, I will suggest you to change the variables or change the function. So assuming that r is given by r divided by square root of r, or r divided by r power of alpha, and then you find alpha, okay, which is usually is alpha is equal to -1. So it will be r divided by r capital, r capital divided by r small. Then you will simplify the equation a little bit. But in general, I don't do that. Let's expand it. So you will get r d2 dr squared of r equal to a constant times r. Do you agree, guys? And dividing both sides again, or you can do the expansions. That will be r squared, second derivative of r with respect to r, plus the other one will be r dr divided by dr minus c times r equal to 0. It's a second order differential equation with the constant coefficients. The singularity, which is regular singularity, is at r equal to 0. What you have to do, you have to do the expansions. Okay. So I will not do the expansions because this is something that we just learned. So the result will be, which is very interesting by itself, the result will be r is equal to, or is given either in two terms, is r power of L or power of minus L minus 1. What is L? L indeed is related to the constant that we had it here. So C is equal to L times L plus 1. So you end up with a series, and you say that this series from the relation between A0 and A1 should be, you know, for A0 and A1, there should be a relationship exactly look like the Bessel function that we done together. We should say that A0 times that coefficient should be equal to 0. And in order to have that coefficient to be equal to 0, the C, that constant, should be given by an integer times another integer value, or two following up integers, which that dictates that C will be given by L times L plus 1. All right. So then substituting in the other expression, what we will get this relation, so which will be 1 divided by sine of theta 1 divided by theta, d theta, sine of theta, d theta divided by d theta minus m square divided by sine square of theta plus the constant. What was the constant? L times L plus 1 equal to 0. So the radial part we solved. Do you want me to solve it, the radial part, or is clear for you guys? Exactly is the same fashion that we solve for the Bessel function. You have two terms that you have to take care, is A0 and A1. And in order to have that identity to be equal to 0, then not A0 or A1 to be equal to 0, what you will end up with, that these constants should be two integer values that are in a row. So it should be given by L times L plus 1. Okay, but I'm sure that you will solve it. If you don't, if you have any problem, just let me know. I will drive it and send it to you. So the only part that is remaining as a puzzle for us is the theta part. Remember, theta is related to that angle from Z. What is the value of theta? Is changing from 0 to pi. Theta is changing from 0 to 1 pi. Okay? Which essentially cosine of theta is bounded between 1 and minus 1. Do you remember? I'm trying to bring up something for you guys that we discussed about that maybe 2 lectures ago, which was having a complete basis between minus 1 and 1. What was that? Legendre polynomial. And you will see that this is a Legendre differential equation. Exactly the same way. But here you have M, which adds another level of complexity, which we call it modified Legendre polynomial. And let's solve that. I mean, maybe we'll go through the details. So let's change the variable. Let's assume that sine of theta, should I change? Let's go. Okay, let's go and choose cosine of theta to be a new variable, which I call it u. Good. Here, theta capital is a function of theta small. Okay, which, as we discussed, theta small is changing from 0 to 1 pi, and therefore cosine of theta is changing from minus 1 to 1. So now I'm changing the variable in such a way that I'm dealing with cosine of theta. Then theta capital is not anymore function of theta small, but is a function of cosine of theta, which is u. So derivative with respect to theta of theta capital now has to be translated in terms of u. So I use the chain rule. So it means that it will be du d theta and d theta capital du. Which means that will be given by, what is the derivative of u with respect to theta? Derivative of cosine respect to theta will be minus sine of theta d theta du. All right. So indeed, d theta can be replaced by minus sine of theta du. Let's do this. So the first term will becomes minus d du of theta. The second term will be d du And that will be 1 divided by theta with the negative sign of sine square of theta. And then I have minus m square divided by sine square of theta plus L times L plus 1 equal to 0. All right. Where? Now, sine d theta, I replace it by d theta. Oh, yes, it will be sine square. Sorry, my bad, my bad. Thank you very much. D theta, the other one doesn't have. No, okay. Minus sign. Thank you. So now let's do a little bit of simplification. The minus sign goes away. That will be d du. Sine square, as I say, minus sign goes away. Sine square will be 1 minus cosine square. That will be 1 minus u square. D du of theta minus m square divided by 1 minus u square plus L times L plus 1. And entire of this will be multiplied by theta equal to 0. Because the theta is in denominator, which I have to multiply. They call that modified Legendre differential equation. Okay. What time is it? 20 minutes. Okay. In 5 minutes, I will conclude just to tell you how to solve these differential equation. Usually what people they do, they will reduce this differential equation to something that we know how to solve it. We solve it for m equal to 0. All right. If you set m equal to 0, then you will get d du 1 minus u square d theta du plus L times L plus 1 of theta equal to 0. This is the ordinary, or let's say the Legendre differential equation that you deal with. That's a Legendre differential equation, not modified one. Okay. What are the solution of that? P L of cosine of theta or PL of u, that we already discussed that. Legendre polynomial. Okay. How do you solve these, guys? Again, we just series expansion. Do that, and you will see with the series expansion, you will get exactly the same expression. Let me check if I have not done any stupid mistakes in the. No, that's all is okay. So that is the way that people they will solve the equation. Okay. So, and when you know the Legendre polynomial for any arbitrary or for any values of m, not only m equal to 0, then that Legendre polynomials will be labeled by another index, which we call it PM of PLM of u, which u was cosine, so that is PLM of cosine of theta. So PLM of cosine of theta, which is a modified Legendre polynomial. They call it modify, or yeah, I think they call it modified Legendre polynomial. That will be a solution to this differential equation that we had it. Remember, the solutions are polynomials. Okay, you can get it from the Frobenius series technique, the same approach that we try. Expand the function around u equal to 0, replace it here. You have two singularities. The singularities, if you look at that expression, guys, or the above expression, the singularities are at u equal to +1 or -1, which are the edges of the domain that you are dealing with. Because we are dealing with cosine of theta, and when theta is changing from 0 to pi, then cosine of theta is changing from -1 to +1. So they are at the edges. So the singularities are fine. Then you do the expansions at u equal to 0, and using this Frobenius series technique, and you will get exactly the expression that we discussed about that. Okay, and we call that Legendre polynomials. Now, for spherical coordinates is very easy, as I said. For the radial part, what was the solution? R power of L, R power of minus L plus -1. All right, those are the two solutions for second order differential equation. What was the solution for azimuthal part? E power of I m phi, e power of minus I m phi. All right. What about the radial part? P L M of cosine of theta. Sorry, what about the theta part, which is given by P L M of cosine of theta? And the combination of these, they will call them solid angle one or spherical harmonics, which we call them YLM of theta and phi. And I will be discussing about that during the next lecture. Just don't forget, when you go home, solve that differential equation that we discussed together, look at the polynomials as well, and we will come back with physical problems that we have to solve and tackle the problems with. Okay? Any questions? I think it's 25 sharp in time this time. That's holding you for long. I will stop the recording. I will see you next lecture.